Hello, so today we're going to talk about atmospheric circulation. So last time we talked about the layers of the atmosphere, and earlier we talked about how energy comes into the Earth and where it goes from there. So now we're going to talk more about how it's circulating while the energy is on Earth in those atmospheric layers. So one thing that's important to understand before we start with this is the difference between weather and climate. So climate is much more long-term than weather. Weather is very short-term. It describes what's happening in terms of temperature, precipitation, air pressure, etc. in one spot at one time. So you might have very different weather than somebody even in the same state as you. And you're going to have different weather from day to day and from season to season. Climate is much more long-term, so we're talking at least decades, usually hundreds to millions of years, looking at temperature patterns, looking at precipitation patterns, and it depends on a lot more things also. So all of these things come into play. So this is one of the things that a lot of the climate change naysayers really don't understand this difference. They'll look at something like the winter we had last year and they'll say, well, with that much snow, there's no way that the world is getting warmer. Well, those are weather patterns. Those were day-to-day things. If we look at temperatures over the last decades and hundreds of years, we can see that everything has been rising. Temperatures have been going up, and quite dramatically actually. So it's really not fitting our normal climate pattern, and that's part of what is a little bit disturbing about it. So let's make sure that we understand this difference between weather and climate, and we're going to talk about both this unit at different times. Alright, another thing we want to kind of make sure we're clear on, latitude and altitude. So latitude is basically how far away from the equator you are. The further you get towards the poles, the higher the latitudes are. And remember that this goes along with this idea of solar radiation. You're getting more solar radiation at those low latitudes towards the equator, less at the poles. Precipitation tends to follow this pattern also. Altitude, on the other hand, is how high you are from sea level, so how high up you go in height. And about every 1,000 feet you go up, the temperature will drop about 3 degrees Fahrenheit. You usually get more precipitation down low in lower altitudes also. So these can both affect weather and climate. The world can kind of be divided up into several climate zones. So we're going to talk about these later in going into your next unit, and we're going to tend to refer to them as biomes, these climate zones. But these really depend on this atmospheric circulation that we're going to talk about today, and all these patterns that we're seeing here will help us explain what's happening in those biomes. So atmospheric circulation depends on 4 major things. Depends on the amount of solar radiation that's being received by an area, the convection that's happening there, something called the Coriolis Effect, and also air pressure patterns. So we're going to talk about all these things today. So if we come back to this idea of solar radiation for a second, remember we talked about at the equator you're getting the most direct sunlight. So because of that you're going to heat up a lot more there, and it sets up these temperature zones. So you have this tropical zone right around the equator, then you have a temperate zone in the middle, and then these polar zones where the sunlight's coming in so indirectly that it's not heating up the area nearly as much. Well, it turns out that this amount of solar radiation actually affects the amount of convection that goes on at each of these sites too. And it sets up these different convection cells around the Earth. You don't need to worry about the names of these, but just know that the convection is kind of split up by latitude. It's not how we would kind of expect to see it, which is you have the warmest parts by the equator and the coldest by the poles, and they're just circulating back and forth from the poles to the equator. It's actually a little bit more complicated because it forms these different zones. But convection is still the same idea. You have hot air that rises because it's becoming less dense. Those molecules are spreading out, so that makes it rise. And then as it travels along, it becomes colder and more dense, and that makes it sink. So that same idea is happening here in the atmosphere, only this also goes along with the idea of humidity, which is how much moisture is in the air. So if we look at this convection current here, it kind of puts it all together. As warm, dry air comes along, it runs across surfaces that are close to the ground where there is moisture. It's going to pick up that moisture and it's going to start to cool off. As it starts to cool, now it's moist, but it's starting to rise because it's cooling. So it's taking this water with it, and that brings it up to the clouds where it condenses when it gets cold enough and falls back down as rain. And then once this energy is up there, these cold molecules are up here, they have heat coming in from space that's warming them up, and they're going to start to sink again as a result. So this convection current is happening, but again, it's kind of all tied in with moisture now. Another important impact on atmospheric circulation is the Coriolis effect. So basically what the Coriolis effect says is that Earth is constantly rotating, and that's of course how we get the times of day. But as it rotates, that rotation of the Earth is actually going to change the way that objects or things behave. So the classic example of this is, say you wanted to launch a missile at somebody. Say we were at the North Pole and you wanted to launch it at someone in Africa. So you would think that you would just launch it straight down your longitudinal line and hit Africa. But you got to remember that the Earth is constantly turning. So if it's turning in this direction, you have to account for that. Because if you were to shoot it just from this area, you would actually miss completely and it would land out in the Atlantic Ocean. So Coriolis effect is basically just that all of the objects that are going on, or all of the different patterns that are going on, are going to be deflected sideways because of the spin of the Earth. So this affects our weather because it will affect the way that the atmosphere circulates. It's going to deflect winds to the right side in the northern hemisphere and to the left in the southern hemisphere. So it's spinning around like this. That's going to make anything that would normally be coming down this way kind of branch off that way instead. And that, I know it doesn't seem like it, but it's to the right in terms of it's more of a clockwise pattern. And down in the southern hemisphere, it's the opposite. It's to the left. It's in a counterclockwise pattern. So this is also why if you flush the toilet in one hemisphere, it'll spin in the opposite direction than in the opposite hemisphere. So you can see how this affects what we call our surface winds. You can see how they're all going at an angle. And I want you to notice too that when you're close to the equator, the angle is smaller. So they're still being deflected off in these directions, but they're not being pushed as far off course. They're almost straight. As you get closer to the poles, the angle gets bigger and the Coriolis effect is greater. And these winds are really being deflected quite a bit. Now, again, here it kind of looks like they're going different directions, but if you look at them overall, these would all form kind of a clockwise pattern. So these in the northern hemisphere are going to the right. And then if you look at these ones down here in the southern hemisphere, they all form this counterclockwise pattern instead. All right, so let's put together what we said so far. So we have these differences in solar radiation coming in. They're creating these different convection currents in different areas where this warm, moist air is rising, dropping off its precipitation, and then falling as cold, dense air as it cools off. This actually also influences the winds that are kind of underneath it, which are these surface winds, or what we'll call prevailing winds. And these flow in different directions around the equator and in different temperature zones. So I want you to take a second. You have this picture. I want you to kind of figure out where all these things are. So pause here for a minute. So around the equator, we have these trade winds that are blowing between 0 and 30 degrees north, and they're called that because the ships that used to sail to trade between different continents would sail through there. Now there is an area at 0 degrees Celsius where 0 degrees, latitude, where there is no wind blowing, and this is called the doldrums, right, in the tropics. So the air here is moving straight up. It's super low pressure, and because of that, you get no wind. Also at the horse latitudes, which are 30 degrees north and south, right here in between the trade winds and the westerlies, there is kind of a sink going on. So you're not going to have a ton of wind here either because the air is sinking right down. It's high pressure. You're going to get a lot of rain in those areas. The westerlies are named because they move from the west. The polar easterlies are the opposite. They're coming from the east. So they're named after the direction they come from. And these are the prevailing winds that kind of drive all of the local winds. All right. Another important thing to understand when we're talking about atmospheric circulation is air pressure. So air pressure is directly dependent on density. Remember we said last time that the closer you are to the ground, the more dense the air is. And as you go up, you get less dense. The molecules get spread out more and more. So people will say the air is thinner up there. And it truly is. It's not as dense. This causes it to be lower pressure as you go up too. When you're down here, you have lots of molecules pushing you down on you. So this is high pressure. When you go up in altitude, you have fewer molecules pressing down, so it's much lower pressure. And it turns out that these pressure zones are super, super important when we talk about weather. They're really what determines your daily weather. So basically what happens is in an area your surfaces are heating unevenly because they have different albedos, they're absorbing different amounts of energy, they're going to heat unevenly. You're going to have cool areas, warm areas, and that's going to impact the air that's directly above them. So a cool surface on the ground is going to cool off the air over it, and remember that cool things are more dense, so they sink. This sinking is pressing down on the air molecules here. So this creates an area of high pressure because you have those molecules pressing downwards. And then over warm surfaces, those air molecules are going to move up, become less dense, and go upwards and rise. And since they're lifting up, there's not as much stuff pressing down. So this is areas of low pressure. These cause particular weather patterns. So you'll see on weather maps, they'll mark areas of high and low pressure. Low pressure is associated with rainy weather because as that warm air rises, it's taking water with it, and then that water can condense into clouds and fall as precipitation. High pressure areas, on the other hand, are really nice weather because here you have all that cold air sinking down that's pressing all that water down close to the earth. It's not allowing it to evaporate up into the sky, so it can't rain. So again, it all comes back to this idea of the convection current, and now the convection current has had an effect on the humidity in areas as well. Now, this convection current keeps happening in many different places, and you actually wind up with these zones on Earth with these different climates because of all these different convection currents going on, again, because of all the pressure differences and temperature differences. And these actually wind up causing certain areas of air, certain air masses is what we call them, that have certain temperature and moisture properties. And you can see by looking at them, they have these abbreviations here that stand for different things, and it's describing what's going on with temperature, what's going on with moisture. So these air masses are usually found in these areas, but they do move around quite a bit, and you can see some of that movement on your map here. And when they move in what we call fronts. So there are different types of fronts that you can see here, and this is going to cause different types of weather. And again, this all comes back to those pressure changes and those convection currents. So pause here for a second, kind of get this down, and just make sure you understand that pressure changes cause convection currents, and these convection currents working together with those pressure changes cause fronts, which changes our local weather. The patterns in that local weather over time would make up our climate for the area. So what we're going to move on to now that we've talked about atmospheric circulation is next time we're going to be talking about ocean circulation instead, and then we're going to pull it all together and look at precipitation patterns that are caused by that. So just make sure you have your notes with you next class, and I'll see you then.